Designing a 2300 amp 208 volt electrical service for a strip mall with 20 stores requires careful consideration of several factors. The goal is to provide reliable power to each store while complying with electrical codes and minimizing installation costs. Several options are available, each with its own advantages and disadvantages. Firstly, consider multiple meter stacks and disconnects. This option involves installing a 2500 amp enclosed switch on the back of the building. Multiple conduits are run from the switch to different meter stacks, and 4 to 600 amp disconnects are installed at each meter stack, feeding 4 meters. While this provides distributed metering, it requires a large footprint and may not be aesthetically pleasing. Secondly, consider a single meter stack and parallel disconnects. This option involves installing a single large meter stack with a total capacity of 2300 amps. A single 2500 amp disconnect feeds the meter stack. Multiple 600 amp disconnects are installed in parallel, each feeding a portion of the stores. This option requires a large meter stack but eliminates the need for multiple conduits and meter stacks consolidating the service entrance. Thirdly, consider dual feed service. This option involves installing 2 smaller transformers, each rated for half the load, which is 1150 amps. These transformers are fed from different points on the primary distribution system. 2 1250 amp disconnects are installed, each feeding 1 transformer, and conduits are run from the disconnects to 2 separate meter stacks. This option provides redundancy and reduces the impact of a transformer failure, enhancing the overall reliability of the electrical service. When designing the electrical service, several factors must be taken into account. The transformer must have sufficient kilovolt ampere capacity to meet the load requirements of all 20 stores. The location of the service entrance and the distance to the stores must be considered to minimize voltage drop and conduit runs. Adequate space must be provided for the disconnects, meter stacks, and conduits to ensure safe and easy access for maintenance. All applicable electrical codes and standards, such as the National Electrical Code, must be complied with to ensure safety and legal compliance. For example, Article 230 covers service entrances, and Article 310 covers conductor sizing and ampacity. Given the preference to avoid a large enclosed switch, the single meter stack and parallel disconnects option is a suitable choice. This design provides a centralized service entrance and eliminates the need for multiple conduits and meter stacks. Here's a more detailed breakdown of the single meter stack and parallel disconnects option. Firstly, select a meter stack rated for at least 2300 amps. Ensure the meter stack is UL listed and approved for the intended application. Secondly, install a 2500 amp main disconnect switch ahead of the meter stack. This provides a means to de-energize the entire service for maintenance or emergencies. Thirdly, run appropriately sized conductors from the 2500 amp disconnect to the meter stack. The conductor size must be based on the 2300 amp load and the ampacity ratings in NEC Table 310.16. For example, if using copper conductors with THHN insulation and a 75 degrees Celsius ampacity rating, you would need multiple sets of 600 kcml conductors per phase. Fourthly, install multiple 600 amp disconnects in parallel at the meter stack. The number of 600 amp disconnects required depends on the load distribution among the 20 stores. If the load is evenly distributed, each disconnect would feed approximately 3 to 4 stores. Fifthly, run appropriately sized conductors from each 600 amp disconnect to the individual store meters. Again, the conductor size must be based on the load requirements of each store and the ampacity ratings in NEC Table 310.16. Sixthly, ensure that all equipment is properly grounded and bonded in accordance with NEC Article 250. This includes grounding the meter stack, disconnects, and transformer enclosure. Seventhly, install appropriately sized overcurrent protection for each disconnect and meter. This protects the conductors and equipment from overloads and short circuits. Eighthly, label all disconnects and meters clearly to indicate which stores they serve. This facilitates maintenance and troubleshooting. Ninthly, conduct a thorough inspection and testing of the entire electrical service before energizing it. This ensures that all equipment is properly installed and functioning correctly. Consider the physical layout of the strip mall when designing the service entrance. Locate the meter stack in a central location that is easily accessible for utility meter reading and maintenance. Provide adequate clearance around the meter stack and disconnects to allow for safe working conditions. Coordinate with the local utility company to determine the point of service and any specific requirements they may have. Obtain all necessary permits and approvals from the local electrical inspector before starting construction. Use high-quality materials and workmanship to ensure the long-term reliability and safety of the electrical service. Consider the potential for future expansion when designing the service. Provide extra capacity in the transformer and meter stack to accommodate future load growth. Select equipment that is easily expandable or replaceable to minimize downtime in the event of a failure. When selecting conductors, consider the ambient temperature and dating factors in accordance with NEC Table 310.15. Use conductors with a higher temperature rating if necessary to ensure that they can safely carry the required current. Consider using aluminum conductors instead of copper conductors to reduce costs. Aluminum conductors have a lower ampacity than copper conductors, so you will need to use a larger size conductor to carry the same current. Ensure that all connections are properly torqued and tightened to prevent loose connections and overheating. Use a calibrated torque wrench to ensure that the connections are tightened to the manufacturer's specifications. Consider using surge protection devices to protect the electrical equipment from voltage surges and transients. Surge protection devices should be installed at the service entrance and at each individual meter. Consider using energy-efficient lighting and equipment in the strip mall to reduce the overall load on the electrical service. This can help to save energy and reduce operating costs. Conduct regular maintenance and inspections of the electrical service to ensure that it is operating properly and safely. This includes checking connections, inspecting conductors, and testing overcurrent protection devices. Keep accurate records of all maintenance and inspections. In addition, consider the environmental conditions at the location. If the strip mall is located in an area with high humidity or corrosive conditions, use equipment that is rated for those conditions. This will help to prevent corrosion and extend the life of the equipment. Ensure that all electrical equipment is properly ventilated to prevent overheating. This is especially important for transformers and disconnects. Consider using a load management system to control the electrical load in the strip mall. This can help to reduce peak demand charges and save energy. A load management system can automatically shed non-essential loads during peak demand periods. Consider using a power quality meter to monitor the electrical service. This can help to identify power quality problems such as voltage sags, swells, and harmonics. Power quality problems can damage electrical equipment and disrupt operations. Ensure that all electrical work is performed by qualified and licensed electricians. This will help to ensure that the work is done safely and correctly. Obtain a certificate of occupancy from the local building inspector before opening the strip mall. This ensures that the electrical service meets all applicable codes and standards. Keep a copy of the electrical plans and specifications on site for future reference. This will be helpful for maintenance and troubleshooting. Train the strip mall tenants on how to operate the electrical equipment safely. This includes showing them how to turn off the power in an emergency and how to avoid overloading the circuits. Provide emergency lighting in the strip mall in case of a power outage. Emergency lighting should be powered by a backup generator or battery system. Install smoke detectors and carbon monoxide detectors in the strip mall to protect the tenants from fire and carbon monoxide poisoning. Ensure that the fire alarm system is properly maintained and tested regularly. Develop an emergency action plan for the strip mall in case of a fire, power outage, or other emergency. This plan should include evacuation procedures, contact information for emergency services, and instructions for shutting off the power and gas. Store flammable materials in a safe and secure location away from electrical equipment. Keep the electrical panels and equipment clear of obstructions. Ensure that there is adequate lighting in the electrical rooms and equipment areas. Use appropriate personal protective equipment when working on electrical equipment. This includes gloves, safety glasses, and insulated tools. Never work on electrical equipment while it is energized unless you are properly trained and qualified. Follow lockout/tagout procedures when energizing electrical equipment for maintenance or repair. This prevents accidental energization of the equipment while work is being performed. Be aware of the potential hazards of working with electricity. Electricity can be deadly if not handled properly. If you are not comfortable working with electricity, hire a qualified electrician to do the work. Remember that safety is always the top priority when working with electricity. It is crucial to select appropriately sized conductors for the service entrance and branch circuits. The National Electrical Code (NEC) provides guidelines for determining the ampacity of conductors based on their size, insulation type, and installation conditions. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. NEC Table 310.16 lists the ampacities of various conductors based on their size and insulation type. The ampacity of a conductor must be derated if it is installed in certain conditions, such as in a conduit with other conductors or in a high ambient temperature environment. NEC Table 310.15 provides derating factors for various installation conditions. The voltage drop in the conductors must also be considered when selecting the conductor size. Voltage drop is a decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that the voltage drop in branch circuits should not exceed 3% and the voltage drop in feeders should not exceed 5%. The conductor size must be increased if the voltage drop exceeds these limits. In addition to the conductor size, the overcurrent protection device must also be sized appropriately. The overcurrent protection device, such as a circuit breaker or fuse, is designed to protect the conductors and equipment from overloads and short circuits. The overcurrent protection device must be sized to protect the smallest conductor in the circuit. The NEC provides guidelines for selecting the appropriate overcurrent protection device based on the conductor size and the type of load. The overcurrent protection device should not be larger than the ampacity of the conductor it is protecting. The overcurrent protection device should be sized to allow for the starting current of motors and other inductive loads. The short circuit current rating of the electrical equipment must also be considered. The short circuit current rating is the maximum current that the equipment can safely withstand during a short circuit. The available short circuit current at the service entrance must be calculated to ensure that the equipment has a sufficient short circuit current rating. The short circuit current rating of the equipment must be greater than the available short circuit current. The electrical service must be properly grounded and bonded to ensure safety. Grounding is the connection of the electrical system to the earth. Bonding is the connection of metallic parts of the electrical system to each other. Grounding and bonding provide a path for fault current to flow back to the source, which causes the overcurrent protection device to trip and de-energize the circuit. The grounding electrode system must be installed in accordance with NEC Article 250. The grounding electrode system consists of a grounding electrode, such as a ground rod or ground plate, and a grounding electrode conductor. The grounding electrode conductor connects the grounding electrode to the electrical system. The metallic parts of the electrical system, such as conduit, enclosures, and equipment, must be bonded together. Bonding ensures that all metallic parts are at the same potential, which reduces the risk of electric shock. The bonding conductors must be sized in accordance with NEC Table 250.102. In summary, designing a 2300 amp 208 volt service for a strip mall requires careful planning and attention to detail. Consider multiple options, select appropriately sized conductors and overcurrent protection devices, and ensure that the electrical service is properly grounded and bonded. Comply with all applicable electrical codes and standards, and prioritize safety throughout the design and installation process.